Welcome back to Understanding Quantum Information and Computation. My name is John Watrous, and I'm the Technical Director for Education at IBM Quantum. This is lesson number 14 of the series, and it's the second lesson of the fourth unit, which is on quantum error correction. In the previous lesson, we took a first look at quantum error correction, including the 9-qubit Shor code, which establishes that quantum error correction is possible in theory. We also discussed the discretization of errors, which allows us to correct for arbitrary quantum errors on qubits by effectively projecting them onto bit flips and phase flips. In this lesson, we'll discuss the stabilizer formalism, which is a mathematical tool through which we can specify and analyze a broad class of quantum error correcting codes known as stabilizer codes. This includes the 9-qubit Shor code, along with many other examples, including codes that are likely to be much better suited to real-world quantum computing devices than the Shor code. Not every quantum error correcting code is a stabilizer code, but many are, including every example that we'll see in this series. There are certainly interesting and potentially useful quantum error correcting codes that aren't stabilizer codes, but they tend to be rather more complicated, and in any case, there's no question that the stabilizer formalism is a cornerstone in the foundation of quantum error correction, and we'll be relying heavily upon it for the remainder of the unit. Here's a brief overview of the lesson. We'll start out with a short discussion of Pauli matrices and tensor products of Pauli matrices, which can represent both operations on qubits as well as measurements of qubits, as I'll explain, and in this context, we often refer to them as observables. We'll then go back and have a second look at the repetition code, and we'll see how we can describe it through Pauli operations and observables. And that will both inform and lead into a general discussion of stabilizer codes, including several examples, basic properties of stabilizer codes, and how we can go about performing the fundamental tasks of encoding, detecting errors, and correcting those errors. We'll begin the lesson with a brief discussion of Pauli operations, mainly to set the stage for the stabilizer formalism, but also to observe a few key facts and establish some basic terminology. First, here are the Pauli matrices, including the 2x2 identity matrix, as well as the 3 non-identity Pauli matrices, which we'll denote by capital X, Y, and Z throughout the remainder of the series. All 4 of these matrices are both unitary and Hermitian, and we can identify them with operations on a qubit, including operations we might choose to perform, as well as errors, as we discussed in the previous lesson. The non-identity Pauli matrices X, Y, and Z anti-commute with one another, meaning that xy is equal to -1 times yx, xz is equal to -zx, and yz is equal to -zy. And you can easily check these relations by doing the multiplications. These anti-commutation relations are very simple, but they're critically important in the stabilizer formalism and elsewhere, and specifically, as we'll see, these minus signs that pop out when we exchange the ordering of 2 different non-identity Pauli matrices in a product correspond precisely to the detection of errors in the stabilizer formalism. We also have the multiplication rules listed here. Each Pauli matrix is its own inverse, which is consistent with the fact that they're both unitary and Hermitian. And if you multiply any 2 different non-identity Pauli matrices together, you'll always get plus or minus I times the remaining non-identity Pauli matrix. In particular, up to a global phase, y is equivalent to x times z, which explains our focus on x and z errors in quantum error correction. X represents a bit flip, z represents a phase flip, and so, up to a global phase, y represents both of these errors occurring on the same qubit. These 4 matrices all represent operations, or errors, or the absence of an error, on a single qubit, but it's often convenient to tensor them together to perform operations or errors on multiple qubits. As a point of terminology, whenever we refer to an n-qubit Pauli operation, we mean a tensor product of any n Pauli matrices, such as the examples shown here. It's also common to use the term Pauli operation when there's a global phase, but to keep things as simple as possible, I'm going to use the term Pauli operation to mean simply a tensor product of Pauli matrices. The weight of an n-qubit Pauli operation is simply the number of non-identity Pauli matrices in the tensor product. For example, the n-fold tensor product of the 2x2 identity matrix with itself is a weight 0 Pauli operation. A tensor product of 2 Pauli X matrices and a whole bunch of identity matrices has weight 2, and so on. Intuitively speaking, the weight of an n-qubit Pauli operation is the number of qubits on which it acts non-trivially. And it's typical that quantum error correcting codes are designed so that they can detect and correct errors represented by Pauli operations up to a certain weight. We can think about Pauli operations in various ways, including as operations performed intentionally by quantum gates, as well as errors. And we'll also see shortly that Pauli operations can describe measurements. Sometimes it's also useful to think about Pauli operations as generators of certain sets in an algebraic sense that you may recognize if you're familiar with group theory. If you're not familiar with group theory, that's okay. It's really not essential for this lesson, but if you're interested in studying quantum error correction in greater depth, you may find that some basic group theory is very helpful for doing that. Anyway, let's suppose that P1 through PR are n-qubit Pauli operations. So P1 is an n-qubit Pauli operation, P2 is an n-qubit Pauli operation, and so on. When we refer to the set generated by P1 through PR, what we mean is the set of all matrices that we can obtain by multiplying these matrices together in any combination and in any order we choose, taking each one as many times as we like. We'll see a few examples in just a moment, but first let me mention the notation that we use to denote this set, the set generated by P1 through PR, and it's P1 through PR separated by commas inside of angled brackets. It does kind of look like we could easily confuse this notation with Dirac notation, but that doesn't generally happen, and this is the traditional notation in group theory. Here's an example of the set generated by x, y, and z. So n is equal to 1 in this example because there are no tensor products, and we're taking all three non-identity Pauli matrices as generators. It turns out that there are 16 matrices that can be generated by forming products that include these three matrices, and you can reason this through the multiplication rules that we saw earlier. Specifically, we can, of course, get x, y, and z, as well as the identity, and in fact we can also get any of these four matrices times I, -1, or -I, and that's it. This set is commonly known as the Pauli group. We could also consider the set generated by just x and z, and we end up getting half of the Pauli group in this case. And one final example, at least for now, we can consider the set generated by x tensor x and z tensor z. So n is equal to 2 in this case, and we end up getting just 4 elements this time, owing to the fact that x tensor x and z tensor z commute with one another. Pauli matrices and n-qubit Pauli operations more generally describe unitary operations, whether they're errors or they're intentional, but they also describe measurements. To be more precise, starting with just the three non-identity Pauli matrices, we can associate each of these matrices with a projective measurement defined in terms of its eigenvalues and eigenvectors, and here on the screen we have spectral decompositions of these matrices that will help to clarify this. In essence, when we refer to an x measurement, a y measurement, or a z measurement, we mean the projective measurement defined by the projections onto the eigenspaces of these matrices, and commonly we think about the eigenvalues as being the corresponding measurement outcomes. For example, an x measurement is a measurement with respect to the plus-minus basis of a qubit, or alternatively we can describe it by the set containing the projections ket plus bra plus and ket minus bra minus. A z measurement, on the other hand, is nothing more than a standard basis measurement, although, like I said, we sometimes identify the eigenvalues with the measurement outcomes, and if we do that, then the outcomes are plus and minus 1, as opposed to 0 and 1, respectively. We can, in fact, do something along these lines for arbitrary Hermitian matrices, and the term observable is commonly used in this situation. For Pauli matrices and n-qubit Pauli operations more generally, we can perform such measurements non-destructively using phase estimation. And just to be sure that this diagram is clear, here we're performing the measurements non-destructively on the top qubit, whereas the bottom qubit is always initialized to a plus state, or in other words, a Hadamard applied to a 0 state, because that's how phase estimation works. Notice that because the eigenvalues are just +1 and -1 in this case, we only need one control qubit, which is the bottom qubit in this diagram. Any more than that would just be a waste because there is only one bit of precision to worry about. The eigenvalue is either +1 or -1, and the measurement is already perfect just like this. The outcome of this measurement, by the way, meaning the standard basis measurement in the circuit, will be 0 for the +1 eigenvalue outcome, which corresponds to the plus state in the case of an X observable, and the outcome is 1 for the -1 eigenvalue, or the minus state in this case. Everything I just said extends naturally to n-qubit Pauli operations, provided that we keep in mind that when we think about an observable, we're talking about measuring the eigenvalues, not measuring with respect to a basis of eigenvectors. For example, consider the 2-qubit Pauli operation Z tensor Z. Once again, there are two eigenvalues, +1 and -1. So the measurement is described by two projections. Notice in particular that the measurement that we associate with this observable is not the same as measuring both qubits with a Z measurement, or in other words, a standard basis measurement, but rather it's a two-outcome projective measurement where the projections are onto the spaces spanned by all of the eigenvectors corresponding to each of the two eigenvalues, +1 and -1. Another way of thinking about this is that the eigenvalues of a tensor product are products of the eigenvalues of the individual matrices that we're taking the tensor products of. And because -1 times -1 is the same as +1 times +1, for instance, this measurement doesn't distinguish between 0, 0 and 1, 1. So if we were to measure, say, a phi plus Bell state with the measurement described by this observable, we would be certain to obtain the outcome corresponding to the eigenvalue +1. And the state would be unchanged, as opposed to collapsing to 0, 0 or 1, 1, which is what would happen if we performed the standard basis measurements on the two qubits. So, a Z tensor Z measurement is not the same thing as performing two Z measurements independently, but we can in fact perform measurements like this using phase estimation in precisely the same way as before, using a single control qubit, as is shown in the circuit diagram, which generalizes to any n-qubit Pauli operation in place of Z tensor Z. When we have just Z Pauli matrices, by the way, we can simplify the circuit like this. And what this reveals, which is also evident from the projections that define the measurement, is that performing a Z tensor Z measurement on two qubits is equivalent to measuring their parity, thinking in terms of the standard basis. And this generalizes to the tensor product of any number of Pauli Z matrices. Next, we'll take a second look at the 3-bit repetition code, this time phrasing it in terms of Pauli operations. This will be our first rather simple example of a stabilizer code, and we'll discuss how to generalize this notion shortly, but it is helpful to see how it works in this simple case first. Recall that when we apply the 3-bit repetition code to qubits, we encode a given qubit state alpha 0 plus beta 1 as alpha 0, 0, 0 plus beta 1, 1, 1, and we'll give this 3-qubit encoding the name psi for convenience. So, by definition, psi is a valid 3-qubit encoding of a qubit state, but if we want to check this, it suffices to check that the following two equations are true. The first equation states that applying Z operations to the leftmost two qubits of psi does nothing to psi, which is to say that psi is an eigenvector of Z tensor identity, or just ZZ identity for short, with eigenvalue 1. And the second equation is similar, except that Z operations are applied to the rightmost two qubits. The idea is, if we think about psi as a linear combination of standard basis states, then the first equation implies that we can only have non-zero coefficients for standard basis states where the leftmost two bits have even parity, or equivalently are equal, and the second equation implies that we can only have non-zero coefficients for standard basis states for which the rightmost two bits have even parity. Another way to think about this is to view these two Pauli operations as observables. And if we were to measure these two observables using the simplified circuit I mentioned just a moment ago, then we would be certain to obtain a measurement outcome corresponding to +1 eigenvalues, because psi is an eigenvector of both observables with eigenvalue 1. But this simplified version of the combined circuit for independently measuring the observables is none other than our parity check circuit for the 3-bit repetition code. And so we see that our two equations together are equivalent to the parity check circuit outputting 0, 0, which is the syndrome that indicates that no errors have been detected. The 3-qubit Pauli operations ZZ identity and identity ZZ are called stabilizer generators for this code. and the stabilizer of the code is the set generated by the stabilizer generators. This set, the stabilizer, is a fundamentally important mathematical object associated with this code, and we'll discuss further the role that it plays as the lesson continues. For now, I'll just point out that we could have made a different choice for the generators. For instance, we could have selected z_identity_z in place of either of the generators we did select, and the code and the stabilizer would be exactly the same. Next, we'll consider bit flip detection for the 3-bit repetition code, with a focus on the interactions and relationships among the poly operations that are involved, namely the stabilizer generators and the errors themselves. Suppose that we've encoded a qubit using the 3-bit repetition code, and a bit flip error occurs on the leftmost qubit. This causes our state psi to be transformed according to the action of an X operation, or X error, on the leftmost qubit. As we already know, we can detect this error by performing the parity checks for the 3-bit repetition code. Or equivalently, we can measure the encoding non-destructively, treating the stabilizer generators as observables. Let's start with the first stabilizer generator and see what happens. Our state has been affected by an X error, and we'd like to understand how the measurement of the stabilizer generator as an observable is influenced by this error. X and Z anti-commute, whereas everything commutes with the identity matrix, and so it follows that ZZ identity anti-commutes with X identity identity, so we get a minus sign when the order is changed. And we also know that ZZ identity doesn't do anything to psi, because psi is a valid encoding of a qubit, and valid encodings are always +1 eigenvectors of both stabilizer generators. That leaves us with negative X identity identity applied to psi, and therefore X identity identity applied to psi is an eigenvector of ZZ identity with eigenvalue -1. We can also do something similar with the second stabilizer generator, but this time the error commutes with the stabilizer generator, and so our corrupted state is again an eigenvector of the stabilizer generator, but this time the eigenvalue is +1. So our corrupted state is an eigenvector of both stabilizer generators, and whether the eigenvalue is +1 or -1 is determined by whether the error commutes or anti-commutes with each stabilizer generator. For the first one, the error and the stabilizer generator anti-commute, and for the second one they commute, and it's always going to be one or the other, because any two poly operations either commute or anti-commute. Meanwhile, the actual state psi doesn't really play an important role here, except for the fact that the stabilizer generators act trivially on this state. So, when we're thinking about the detection of errors, we really don't need to concern ourselves with the specific encoded state. All that matters is whether the error commutes or anti-commutes with each stabilizer generator. So let's make a table that has one row for each stabilizer generator and one column for each error. Here I've only included the errors corresponding to a single bit flip, as well as no error at all, which is indicated by the identity tensored with itself 3 times. We could add more columns for other errors if we wanted, but for now we'll focus on just these errors. The entry in the table is either +1 or -1, depending on whether the error and the stabilizer generator commute or anti-commute. So, for each error in the table, we can look at the corresponding column to see how that error will transform any given encoding into a +1 or a -1 eigenvector of each stabilizer generator. These columns correspond precisely to the syndrome we would obtain from the parity checks, which are equivalent to the non-destructive measurements of the stabilizer generators as observables. Of course, the entries in this table are +1s and -1s rather than 0s and 1s respectively, and if you prefer, you can think about the syndromes as being the corresponding binary strings rather than columns of +1s and -1s, but there's a direct correspondence, and just to make the connection between the syndromes and the eigenvalues more clear and direct, I'm going to refer to these vectors of +1s and -1s as syndromes. As before, the syndromes tell us something about whatever error took place. And in particular, if we know that one of these 4 possible errors occurred, the syndrome indicates to us which one it was, and we can correct it by applying the error again, if we choose. Next, I'll say just a little bit more about the syndromes, and in particular, we'll take a closer look at their algebraic aspects. Our encodings are 3-qubit states, so they're unit vectors in an 8-dimensional complex vector space, And what the four possible syndromes do is to slice this 8-dimensional space up into 4 2-dimensional subspaces, meaning that the vectors in any one of these subspaces will always give us the same syndrome. In more detail, this diagram illustrates how the 8-dimensional space is divided up. Each stabilizer generator splits the space into 2 subspaces of equal dimension, namely the space of +1 eigenvectors and the space of -1 eigenvectors. For example, the +1 eigenvectors of ZZ identity are linear combinations of standard basis states for which the leftmost 2 bits have even parity, and the -1 eigenvectors are linear combinations of standard basis states for which the leftmost 2 bits have odd parity, and the situation is similar for the other stabilizer generator, except that it's the rightmost 2 bits rather than the leftmost 2 bits. So, these 4 subspaces are easy to describe in this case, owing to the fact that this is a very simple code. In particular, the subspace corresponding to the syndrome +1+1 is the space spanned by ket 000 and ket 111, which is the space of valid encodings, and that's called the code space. And in general, the spaces are spanned by the standard basis states that are shown in the corresponding squares. Although it's not necessarily as clear or as easy to see, the syndromes also partition all of the 3-qubit Pauli operations, which represent the possible Pauli errors that could take place, into 4 equal-sized collections, depending upon which syndrome that error would cause. For example, any Pauli operation that commutes with both stabilizer generators results in the syndrome +1+1, and among the 64 possible 3-qubit Pauli operations, there are exactly 16 of them in this category, including the 3 that are mentioned on the screen, and likewise for the other 3 syndromes. That's not obvious, but it is true, and this basic property that the syndromes partition both the state space in which the encodings live and all of the possible Pauli errors in the space into equal-sized pieces is something that's true in general for stabilizer codes, which we'll soon define precisely. Although it's mostly just an aside at this point, it's worth mentioning that Pauli operations that commute with both stabilizer generators, or equivalently Pauli operations that result in the syndrome +1+1, but are not themselves proportional to elements of the stabilizer, turn out to behave just like single-qubit Pauli operations on the logical qubit that we encoded. For example, XXX commutes with both stabilizer generators, but it's not proportional to any element of the stabilizer, and indeed it's clear, if you think about this code for a moment, that the effect that this operation has on an encoding is equivalent to an X-gate on the logical qubit that was encoded. And again, this is something that generalizes to all stabilizer codes. Now it's time to define stabilizer codes in general, and the way that it works is that we do something completely analogous to what we just discussed for the 3-bit repetition code, except that we pick different stabilizer generators, which I'll refer to as P1 through PR for the sake of this explanation. These stabilizer generators must all be n-qubit Pauli operations, where n is the number of qubits used for the encoding, and we can't just pick any old set of stabilizer generators. They have to satisfy a few basic conditions. First, the stabilizer generators must all commute with one another. In the case of the 3-bit repetition code, we didn't bother to take note of this, but it is straightforward to observe that ZZ identity and identity ZZ do in fact commute, because Z commutes with itself and everything commutes with the identity. For stabilizer codes with more complicated stabilizer generators, on the other hand, including codes where we have both X's and Z's appearing in the stabilizer generators, this is an important condition that needs to be checked. One way to think about the need for this condition is that we're going to be treating the stabilizer generators as observables, and by requiring that they all commute, we're ensuring that the order in which we perform these measurements doesn't matter. Second, the stabilizer generators must form a so-called minimal generating set, which means that if we removed any one of them, we'd get a smaller stabilizer. And one way to express this mathematically is shown here on the screen. Strictly speaking, this condition isn't really essential to the way that a stabilizer code works in an operational sense, and sometimes it does make sense to think about non-minimal generating sets, as we'll see in the next lesson, but for the sake of analyzing stabilizer codes and explaining their properties, we're going to assume that this condition is in place. Basically, this condition guarantees that each observable that we measure to obtain the syndrome is adding information about possible errors, as opposed to being redundant and giving results that could easily be inferred from the other stabilizer generators as observables. And finally, it must be the case that at least one non-zero vector is fixed by all of the stabilizer generators. And that turns out to be equivalent to demanding that -1 times the identity on n qubits is not contained in the stabilizer. That's not obvious, but the point is that it is possible to choose a minimal generating set of n-qubit Pauli operations that all commute with one another, and yet no vector is simultaneously a +1 eigenvector of all of them, and we don't want to concern ourselves with this possibility because codes where there aren't any valid encodings aren't interesting. So those are the requirements on the stabilizer generators for a stabilizer code. And if we do have a set of generators that satisfy these conditions, then we have a valid stabilizer code, and we can consider its properties. There are many different stabilizer codes with various properties that make them interesting or not, but they all satisfy certain basic properties that are reminiscent of the ones that we've already observed for the 3-bit repetition code. We'll take a look at some examples shortly, but before that, let me mention that when we refer to the code space of a stabilizer code, we mean the subspace of the n-qubit state space that includes every vector that's simultaneously a +1 eigenvector of every one of the stabilizer generators. This is the subspace of the n-qubit state space in which valid encodings live, and we'll have more to say about this subspace as the lesson continues. Now let's take a look at a few examples of stabilizer codes. Here's the example we've already discussed, the ordinary 3-bit repetition code. And we can also express the modified version of that code from the previous lesson, which can detect a phase flip instead of a bit flip, as a stabilizer code, as is shown here. This time, the stabilizer generators measure XX observables rather than ZZ observables, so these are basically parity checks in the plus-minus basis rather than the standard basis. In both cases, we can immediately see that we have a valid stabilizer code because the stabilizer generators commute, these are minimal generating sets, and the code space is non-trivial, as we already know, but we can also see pretty clearly that we can't generate -1 times the identity. And here's the 9-qubit Shor code, which is also a stabilizer code, expressed by stabilizer generators. In this case, we basically have 3 copies of the 3-bit repetition code, one for each of the 3 blocks of 3 qubits, as well as the last 2 stabilizer generators, which take a form that's reminiscent of the circuit that we saw in the previous lesson for detecting phase flips for this code. Another way of thinking about these last 2 stabilizer generators is that they take exactly the same form as we have for the 3-bit repetition code for phase flips, except that we substitute XXX for X. And the reason for that is that XXX corresponds to an X operation on the logical qubit encoded using the 3-bit repetition code. But that's an aside, and it's not something to worry about right now in case it isn't clear. Next, we'll take a look at a few more examples, but before that, let me mention that people often omit the tensor product symbols when describing stabilizer codes because it tends to make them easier to read. So here's what these codes look like without the tensor product symbols. But of course, these are tensor products and not ordinary matrix products, for instance. We're just leaving out the tensor product symbols so that it's less cluttered and the patterns are more clear. Here's another example. It's called the 7-qubit Steen code, and it has some pretty remarkable features. We'll come back to this one from time to time throughout the remaining lessons of the unit, but for now, we can simply verify that it is a valid stabilizer code. In particular, the first 3 stabilizer generators clearly commute with one another because Z commutes with itself and the identity commutes with everything, and the situation is similar for the last 3. So it remains to check that if we take one of the Z stabilizer generators and one of the X stabilizer generators, then they commute, and it's easy enough to go through the 9 possible pairings to check that. In all of these cases, we'll always have an X and a Z matching up in the same position an even number of times. So the 2 generators will commute just like XX and ZZ commute. It's a minimal generating set, and it has a non-trivial code space, but I won't try to argue that in this video, and instead I'll leave that for you to think about if you wish. The 7-qubit Steen code is similar to the 9-qubit Shor code in the sense that it encodes a single qubit and allows for the correction of an arbitrary error on 1 qubit. But it only requires 7 qubits rather than 9. That's not the fewest number of qubits required for an error correcting code to encode a qubit and correct for an arbitrary error on a single qubit. Here's a stabilizer code that's usually just called the 5-qubit code that also encodes a single qubit and can correct an arbitrary single qubit error, and 5 is the smallest number of qubits for which this is possible. Here's another example of a stabilizer code, although it isn't really a code, so to speak, in the sense that the code space is one-dimensional. In particular, the code space for this code is the space spanned by an E-bit, or in other words, a Phi plus Bell state. So you can't actually encode any qubits using this code, but it's still a valid stabilizer code where the code space happens to be one-dimensional. And it's possible to do something similar for a GHZ state. So those are some examples of stabilizer codes, and we'll see infinitely many more examples in the next lesson. Suppose that we're given a stabilizer code. A natural question to ask about it, perhaps the very first question that comes to mind, is how many qubits does it encode? That question has a very simple answer, and to explain it, let's be precise about the stabilizer code being considered. We have R n-qubit stabilizer generators, P1 through PR, that satisfy the 3 requirements that I mentioned earlier, namely that the stabilizer generators all commute with one another. This is a minimal generating set, so we wouldn't get the same stabilizer if we removed one of the generators, and there's at least one non-zero vector in the code space. As the theorem shown on the screen indicates, it must then be that the code space of the stabilizer code has dimension 2 to the power n minus r. Or another way of saying that is that we can encode n minus r qubits using this code. So, intuitively speaking, we have n qubits in our encodings, and each stabilizer generator effectively takes a qubit away in terms of how many qubits we can encode. This theorem isn't too hard to prove, and I'll show you a proof in just a moment, but first we'll take a look at just a few examples, starting with the ordinary 3-bit repetition code. We have 3 qubits in our encodings, so n is equal to 3, and there are r equals 2 stabilizer generators, and so we can encode 1 qubit using this code. Notice that this is not about which or how many errors can be detected or corrected. That's a different matter. This is just a statement about the dimension of the code space. For another example, consider the 5-qubit code. Here we have 5 qubits and 4 stabilizer generators, so once again, the code space has dimension 2, which means that we can encode 1 qubit using this code. And one more example for now. For the E-bit stabilizer code, we have 2 qubits and 2 stabilizer generators, so the code space is one-dimensional, and as I mentioned earlier, it's the space spanned by the Phi plus Bell state. We'll see more examples as we continue on, including codes where we can encode more than 1 qubit, but for now, let's see how we can prove the theorem. The first thing that we need to observe is that because the stabilizer generators commute and form a minimal generating set, and because every Pauli operation is its own inverse, every element in the stabilizer can be expressed in a unique way as a product, where we raise each stabilizer generator pk to the power ak, where each ak is either 0 or 1, and then we multiply the results together. Another way to say this is that we get every element of the stabilizer by multiplying together some subset of the stabilizer generators, and we never get the same stabilizer element from different subsets. And one thing that this implies is that the only way to express the n-qubit identity operation in this way is to take all of the powers to be 0. Next, let's define pi k to be the projection onto the +1 eigenspace of pk for each k from 1 to r, and there's a simple formula for this projection. We can simply average pk with the identity on n qubits, which effectively leaves the +1 eigenvalues alone and shifts all of the -1 eigenvalues to 0 eigenvalues. Now, the code space is defined as the set of all vectors that are simultaneously +1 eigenvectors of all of the stabilizer generators. Given that the stabilizer generators commute, the projections must also commute, and that implies that the product of these projections is also a projection, and in particular, it's the projection onto the intersection of the subspaces that the individual projections project onto, or in other words, it's the projection onto the code space. We can expand out this product, and what we get is the average over every element of the stabilizer. And finally, because the dimension of any subspace is equal to the trace of the projection onto that subspace, we find that the dimension of the code space is the average of the traces over the elements of the stabilizer. But with the exception of the n-qubit identity operation, all of the elements of the stabilizer must have trace equal to 0, because the three non-identity Pauli matrices all have trace equal to 0. The trace of the n-qubit identity operation is 2 to the n, and so we find that the dimension of the code space is 2 to the n minus r, which proves the theorem. Next, I'll say just a little bit about how qubits can be encoded using stabilizer codes, but to do that, we first need to introduce Clifford operations. Clifford operations are unitary operations on any number of qubits that can be implemented by quantum circuits with a restricted set of gates, namely Hadamard gates, S gates, and controlled NOT gates. Notice that T gates are not included, nor are Toffoli gates or Fredkin gates, and not only are those gates not included in this list, but in fact it's not possible to implement those gates using the ones listed here, so they're not Clifford operations. Pauli operations, on the other hand, are Clifford operations, and specifically they can be implemented using sequences of Hadamard and S gates. So that's a simple way to define Clifford operations, but it doesn't really explain why they're defined in this way or what's special about this particular collection of gates. Here's the real reason that Clifford operations are defined like this. Up to a global phase, the n-qubit Clifford operations are precisely the unitary operations that always transform Pauli operations into Pauli operations by conjugation. To be more precise, an n-qubit unitary operation U is a Clifford operation up to a global phase factor if and only if, for every n-qubit Pauli operation, conjugating that Pauli operation by U gives us plus or minus 1 times some possibly different n-qubit Pauli operation. You can easily check that this property is true for Hadamard gates, S gates, and CNOT gates, so it necessarily holds for circuits built from these gates. What's harder to prove is that it goes in the other direction, which is that if we're given a particular n-qubit unitary operation U that satisfies this property, then it must be possible to implement it up to a global phase using just Hadamard, S, and CNOT gates. I won't go through the proof of that implication, but it is true, and you can look it up if you're interested. Clifford operations are not universal for quantum computation, meaning that we can't run arbitrary quantum computations using just Hadamard, S, and CNOT gates. In fact, for a given value of n, there are only finitely many n-qubit Clifford operations. So, it's a discrete set of operations. So unlike a universal set of quantum gates, we can't approximate arbitrary unitary operations to any desired level of accuracy. And in fact, performing Clifford operations on standard basis states, followed by standard basis measurements, can't allow us to perform computations that are outside of the reach of classical algorithms, because we can efficiently simulate computations of this form classically. This fact is known as the Gottesman-Knill theorem, and the standard proof of that theorem is in some sense based on the stabilizer formalism. In particular, the way that it works is that we can keep track of the way that Clifford operations transform Pauli operations by conjugation, which can be done efficiently, and then infer from that what the computations do to qubits. So what does this have to do with stabilizer codes? Well, a stabilizer code provides us with a code space of a certain dimension, and we have the freedom to use that code space however we choose. So nothing forces us to encode qubits into that space in a specific way, but it will always be possible to perform an encoding using a Clifford operation as the encoder. That's nice because Clifford operations are relatively simple compared with arbitrary unitary operations. There are ways to optimize their implementation, which works along similar lines to the proof of the Gottesman-Knill theorem, and as a result, circuits for implementing them never need to be all that large. In particular, we can always perform an encoding using a Clifford operation that requires a little bit less than a quadratic number of gates, because that's actually true of every Clifford operation. So the upshot is that for a given stabilizer code, it's always possible to encode qubits efficiently using that code, and the mathematical tools that are useful for understanding Clifford operations can help with this process. For example, here's an encoder for the 7-qubit Steen code. It's a Clifford operation, and as it turns out, this one doesn't even need S-gates. For general stabilizer codes, error detection works in the following way. As before, we'll assume that we have n-qubit stabilizer generators P1 through PR, and we'll let E be an n-qubit Pauli operation representing a hypothetical error on an encoding. We're only considering Pauli operations as errors, by the way, because the discretization of errors works in the same way for arbitrary stabilizer codes as it does for the 9-qubit Shor code. The way that we check for errors is to measure each of the stabilizer generators as observables. There are R stabilizer generators, so this means R outcomes, where each one is a +1 or a -1, or a binary value if you prefer to associate 0 with +1 and 1 with -1, and these R outcomes together form the syndrome, just like we had for the 3-bit repetition code when R was equal to 2. In general, there are 3 possible cases for the error E in terms of its detection, and they are as follows. First, it could be that E is in the stabilizer, meaning that it's possible to generate E from the stabilizer generators, or slightly more generally, it could be that E is equivalent to a stabilizer element up to a global phase. In this case, E isn't really an error at all because it has no effect on the code space other than to possibly inject a global phase, which doesn't have any effect. So we don't need to worry at all about errors like this. Whatever non-trivial action it might have happens outside of the code space, so it doesn't concern us. Much more of a concern is the possibility that E is not in the stabilizer, even up to a global phase, but nevertheless it does commute with every single one of our stabilizer generators. Remember that it's the anti-commutation of the error with the stabilizer generator that causes a -1 to appear somewhere in the syndrome, but that doesn't happen in this case. So this is an error that actually does change vectors in the code space in some non-trivial way, and we know this because otherwise it would be proportional to a stabilizer element, but it goes undetected by the code. So this is the bad case. We have an error that may potentially be changing whatever quantum information we've encoded, but the code is oblivious to this fact. For example, for the 3-bit repetition code, XXX falls into this category. And the last possibility is that the error E anti-commutes with at least one of the stabilizer generators. And this means that the code detects this error, because we'll get a syndrome with at least one -1 somewhere in it, which indicates that something is wrong and we'll need to try to correct this error somehow. So those are the possibilities. As a point of terminology, when we refer to the distance of a stabilizer code, what we mean is the minimum weight of a Pauli operation that falls into the second category, meaning that it changes the code space in some non-trivial way, but the code doesn't detect this. And when we say that a stabilizer code is an NMD stabilizer code, using double square brackets as is shown on the screen, what that means is that encodings are n qubits in length. The code is capable of encoding m qubits, so the code space has dimension 2 to the m, and its distance is d. So an error has to have weight d or more to change the logical state of whatever qubit we've encoded without being detected as an error. We'll now take a look at the 7-qubit Steen code as an example, and we'll determine what its distance is. Here are the stabilizer generators for this code, and recall that the distance is the minimum weight of an n-qubit Pauli operation that commutes with all of the stabilizer generators, but is itself not in the stabilizer, nor is it proportional to an element of the stabilizer. What we'll determine is that this code has distance 3. The way that we'll determine this is to first consider any Pauli operation having weight at most 2, and we'll conclude that the only way that it can compute with all 6 stabilizer generators is for it to be the identity, which is always an element of the stabilizer. So let's suppose that the possibly non-identity Pauli matrices that form this operation, which we'll call P and Q, appear in the leftmost 2 positions. This is just one case, and we do have to consider all of the other possible locations for these possibly non-identity Pauli matrices, but the argument is basically the same for all of the possible locations. Well, by assumption, this operation commutes with all 6 stabilizer generators, so in particular it commutes with this one, and it also commutes with this one. Q lines up with the identity matrix in both of these generators, which is why we chose these two. And we have identity matrices in the rightmost 5 positions of this error, and so we conclude that P must commute with both X and Z, because otherwise this error would anti-commute with one of these two generators. But the only Pauli matrix that commutes with both X and Z is the identity. So P must be the identity. And now that we know that, we can choose 2 more stabilizer generators that have an X and a Z in the second position from left. And we can draw a similar conclusion about Q. So there's no way for a weight at most 2 error to go undetected by this code, unless it's just the identity operation, which is in the stabilizer, so this isn't actually an error. On the other hand, there are weight 3 Pauli operations that commute with all 6 of these stabilizer generators, but aren't proportional to stabilizer elements, and here are 2 examples. So we've concluded that this code has distance 3. The last thing that we'll discuss in this lesson is correcting errors for stabilizer codes. As usual, we'll assume our code is specified by n-qubit stabilizer generators, P1 through PR, and let's start by thinking a little bit about all of the possible errors that could take place. There are 2 to the R possible syndromes, and as I mentioned earlier in the lesson, these syndromes partition all of the possible n-qubit Pauli operations into equal-sized collections, so that means 4 to the n divided by 2 to the r Pauli operations within each set. So when we see a particular syndrome, it could be that any one of these 4 to the n divided by 2 to the r errors is responsible. We are overcounting a little bit here though, because some of these errors have exactly the same effect on the code space. In particular, if we have an error E and we multiply E by any stabilizer element S, then we're going to get another error that has exactly the same effect in the code space as E, so these are equivalent errors. The stabilizer has 2 to the r elements, and if we account for this, then we find that for each syndrome, there are 4 to the n minus r inequivalent classes of errors that could have caused that one syndrome. And what that means is that unless r is equal to n, in which case we have a one-dimensional code space, and therefore can't encode any qubits at all, it's not going to be possible to correct every error that we can detect. Instead, what we have to do is choose just one correction operation for each syndrome in the hopes of correcting just one class of equivalent errors. So how should we choose what correction to perform for each syndrome? A natural strategy is to choose the lowest weight Pauli operation that causes whatever syndrome we measure, with the idea being that lower weight Pauli operations represent more likely explanations for that syndrome. This might not actually be the case for some noise models, and another natural strategy is to somehow compute the most likely error that causes the given syndrome, but for now, we'll just consider the strategy where we attempt to correct errors by selecting the lowest weight Pauli operation causing the syndrome. For a distance d stabilizer code, this strategy will always allow us to correct errors having weight strictly less than half of d, or in other words, weight at most d minus 1 over 2, and I'll explain briefly why this is. This will show, for instance, that the 7-qubit Steen code can correct for any weight 1 Pauli error, and by the discretization of errors, this means that just like the 9-qubit Shor code, the Steen code can correct for an arbitrary error on 1 qubit. So here's how this works. Consider that this circle represents all of the possible Pauli operations that result in the all plus 1 syndrome, which is the syndrome that suggests that no errors have occurred and nothing is wrong. Among these operations, we have elements of the stabilizer, or really operations that are proportional to elements of the stabilizer, and we also have non-trivial errors that change the code space somehow, but they aren't detected by the code. And we know by the definition of distance that every Pauli operation in this category must have weight at least d, because d is defined as the minimum weight of these operations. We also have Pauli operations that cause other syndromes to appear, and we could consider each syndrome in turn if we wish, but here we're just imagining that one such syndrome S has appeared. Now, imagine that E is an error in this category that has weight strictly less than half of the distance d. Well, we don't know that this is necessarily the minimum weight Pauli operation in this circle, so let's take C to be the minimum weight operation in this set, or one of them in case there's a tie. So it could be that C is equal to E, or possibly not, but because C has minimal weight, we know that it can't possibly have weight larger than the weight of E, because C is also in the set and it has minimal weight. So the correction operation C must have weight strictly less than half of D. So what happens if we apply this correction C to whatever our state becomes after the error E occurs? The answer is that the state that we obtain is C times E multiplied to the original encoding, because we first multiplied by E, that was the error, and then we multiplied by C to try to correct it. And this product must be in the stabilizer, or proportional to an element of the stabilizer, and here's why. First, because E and C give us the same syndrome, C times E must give us the all plus 1 syndrome. That's because for a given stabilizer generator, either C and E both commute with that generator, or they both anti-commute. It has to be the same for both because the syndromes are the same. And if you think about that for just a moment, it implies that C times E must commute with all of the stabilizer generators. And finally, C times E has to be down in the stabilizer because its weight can't be larger than the sum of the weights of C and E, and so its weight is strictly less than D. And this means that we successfully correct E, because applying E followed by C does nothing to the code space. So that's great, but there's just one problem. And that is that for stabilizer codes in general, it's a computationally difficult problem to compute the lowest weight poly operation causing a given syndrome. And indeed, that's true even for classical codes, which in this context we can think about as stabilizer codes where we only have identity matrices and poly-Z matrices appearing as tensor factors within the stabilizer generators. So, unlike the encoding step, Clifford operations don't come to our rescue this time, and the only reasonable solution is to choose specific codes for which good corrections can be computed efficiently. And there's no recipe for this. Simply put, devising stabilizer codes like this is part of the artistry of quantum code design. And that is a good place to stop for this lesson. I hope you will join me for the next lesson, in which we'll take a look at some specific quantum code constructions, including codes that illustrate the artistry of quantum code design in a pretty spectacular way. Goodbye for now.